Hi, welcome to my channel JaberTime. Today I'm going to go over power functions and end behavior. These two graphs, they show clearly about the even power functions and the odd power functions. How do they look like and how do they behave towards positive infinity and negative infinity. Let's get started. Power functions and polynomial functions. Power functions, as a definition. A power function is a function that can be represented in the form f of x equals k times x to the power p. That's how it looks like, where k and p are real numbers, and k is known as the coefficient. Some quick examples. All these are power functions. This is clearly a power function, this is clearly a power function, and this one. Even this one, this is like 1 times x to the power 0, where p is 0, which is a real number. What about 1 over x? What about the cubic root? Well, here we go. We need to see if we could see it of this format. Well, 1 over x could be written as 1 times x to the power negative 1. Yes, it's a power function where p is negative 1. Cubic root of x will be 1 times x to the power 1/3. So yes, p is 1/3, which is a real number, and k is 1, which is the coefficient, and those are power functions. What about functions that they are not power functions? How can we identify them and tell that they don't look like this? Here we go. Examples on not power functions. The main one is 2 to the x. It might look like, or some students might make a mistake and pick on this one as a power function, but it's not. Why? Well, the reason is so clear. This is an exponential function, not a power function. 2 to the x is like multiplying by 2 and 2 and 2 and 2, so it's called doubling. 2 to the first, 2 to the second, 2 to the third. So we're going from 2 to 4 to 8 to 16 and so on. On the left side, it goes down. It's not like a parabola. Why? 2 to the power negative 1 is 1 over 2. 2 to the power negative 2 is 1 over 4. So it's called exponential function. Well, there's a big difference between 2 to the x and x to the 2. I know somehow they look alike, but not really. This is a parabola on the left, and this is an exponential function on the right side, exponential growth. Parabola goes like a U shape, and this one looks like of this type. Here's some quick example or practice about power functions. True or false? Quick. Here's the first one. First one is true. X to the second, one of the basic ones that we usually start teaching in power functions. That is true. Why? Because it just looks like k times x to the power p, where k is 1 and p is 2. How about 2 to the x? We just talked about that. It's not. It's called exponential function. How about 2x to the second times 4x to the third? Well, it's not fully clear like this, but we could simplify it. We could multiply 2 times 4, which is 8. Add the exponents, because that's how we multiply x to the second times x to the third. 2 plus 3 is 5. Now it looks exactly like this. So yes, it is true. It's a power function. How about this one? Well, this one is not. This is one of the titles in the previous slide that says power functions and polynomials. This is a polynomial. It's not a power function. So false, and the reason why it's called polynomial. Well, this one cannot be looked at as k times x to the power p. So what do we call it? We call it rational function. Now let's look at the other part of the title for this video, which is called end behavior of power functions. End behavior. Basically, we're going to focus on two types, which is even power functions, that they all look like this. And this is a great example. The normal x to the second, the one that we're used to, x to the fourth, and x to the sixth. And each one is in different color. The U shape is in green, but the difference now when you go to blue, which is x to the 4, after 1 it's steeper. it grows up faster. Same thing after -1, because negative is not going to make any difference. When you plug in numbers like -2, it's going to change to positive. Now, what happens for the blue one between 1 and -1, it's lower than green. It's lower values. Why? Because here you're going to plug in, for example, like half times half times half times half. It's 1/16. Compared to here, it's half to the second, which is half times half, which is 1/4. So when you multiply half by itself 4 times, it's lower value. When you multiply half by itself 6 times, it's even lower. You could see the red is the lowest between -1 and 1. And it's almost like, we call it, it flattens towards the origin. It looks like it's going to touch the x-axis more than once, but that's not true. If you zoom in, if you do the math, it only touches the x-axis at the origin, all of them. That is even power functions. Let's talk about end behavior. How do you identify the end behavior? Well, it looks like as x approaches -infinity or as x approaches positive infinity, both ways the values are going up to infinity. So we say as x approaches either positive infinity or negative infinity, right or left, the graph goes all the way up to infinity. Now let's look at odd power functions. On the negative side, instead of going up, it stays negative. That's why it is graphed this way. It's not a parabola anymore, because negative stays negative on the left side, because you're multiplying negative by itself an odd number of times. Same idea about 1 and -1. When you are between 1 and -1, when dealing with fractions, this will be lower. The blue one is lower than the green one. It's kind of hard to see, but I could see the red one is lower than the green one. So that's the normal, if you call it normal, or the standard. That would be lower right here. That will be even lower. After 1, this is the standard. X to the 5th will be steeper, higher, and x to the 7th will be even higher. So what about the end behavior model? Going to -infinity, as x approaches -infinity, we're going down. So we are saying f of x goes to -infinity. And as x approaches positive infinity, we're going all the way up. So we call it positive infinity. That is if they are all like x to the power 5 and x to the power 4, which means the leading coefficient, or k, is +1 or positive in general. So if k is positive, that's how the even power functions looks like, and that's how the odd power functions looks like. In case if k is negative, which we talked about this earlier, so I'm not going to read that. When k is negative, that's not going to open up, that's going to open down. And when k is negative, that's not going to look like this. That's going to be flipped up, and that's going to be flipped down, so it's going to go just like this. Here we go. That's how it should look like. That's the difference between if k is negative and k is positive. In this case, as x approaches -infinity or positive infinity, both ways f of x goes to -infinity. In this case, as x approaches -infinity, f of x approaches up to infinity. It's right there. And as x approaches infinity, f of x approaches -infinity. That is in behavior model, and those are examples of power functions. That should do it for this video, and I'll see you in the next one. Thank you.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.